This is my high school graduation cap, and this is my undergrad graduation cap. This is a brain candle that actually lights up and changes color. This is my Armenian flag. It is my Armenian swag. These snowmen hang upside down because my sister spent a month every single night flipping it upside down to make me upset. So eventually I caved in and I keep it upside down now. I use this super cool color changing galaxy light as a nightlight because I get super bad nightmares. And the last useless thing that you didn't want to know but I'm going to tell you about in this video is the Diels Alder reaction. So sit tight and welcome to part 1. Let's get started. So today we're doing Diels Alder, and I know it's been a little bit confusing, and again, it's one of those topics that look really weird and really complicated, but I promise it's not as bad as it seems. We're going to make it super simplified here. So we have a diene, such as this one, that has all this extra electron density, so it's going to be attracted to this double bond, and this will be attracted to the other end. And essentially, we're going to have all of these electrons move around in a circle, and we end up creating a 5-membered ring. So we have these bonds from the original. We just created these bonds. And then we have this bond from the original as well. And then we must remember that we created a double bond here. As you guys can see, these electrons went in to make the double bond. And we had no substituents, so this is our product. We will go over the mechanism in a little bit more detail, but first I want to go over some technical stuff. So when we do this reaction, it is a reaction between the diene and the dienophile. And we're going to discuss what exactly those things are. So the diene, our diene, as the name states, will be any conjugated diene, which, if we remember from a little bit earlier, is a molecule that has 2 double bonds that are 1 single bond apart. The dienophile, on the other hand, can be any alkene or alkyne. And we know that an alkene is a double bond, and an alkyne is a triple bond, like so. Cool. And so as we drew here, we can see that this diene was the first one to give its electrons up, so it will be the nucleophile. And that would mean that this is the electrophile because it's the one being attacked. One thing I do want to note, though, is that, okay, in real Diels Alder, in complicated Diels Alder, there's a bajillion different rules and there's a bajillion ways to do this. But for the purposes of this class, we're going to pretend real organic chemistry doesn't matter. We only care about Orgo 2. So with that kind of context, these are the rules I'm giving you. Okay. So the diene has to actually have a specific conformation in order to react, and it has to be in the S-cis conformation. And as we saw up here, S-cis just means that the 2 double bonds are pointing the same direction. The dienophile, however, we're not going to do conformation, we have to actually look at configuration. And if you guys remember from previous videos, configuration is looking at the priority groups on each side and figuring out if they're pointing the same or opposite directions. In the case of the one drawn above, we don't really have that because it's all hydrogens. There are no priority groups. But in general, we must maintain configuration. So what this means is that if our double bond is trans, it must end up with a trans product. And the same would also work the other way around. So if we had a cis double bond, we would end up with a cis product. The last thing we're going to talk about in this little section is electron donating and withdrawing groups. So dienes will favor electron donating groups. And the reason they want electron donating groups is because they are the nucleophile, so they want more electron density. And electron donating groups do exactly that. They give more electron density. And that allows it to be a stronger nucleophile. On the other hand, our electron withdrawing groups will be favored by the dienophile, and that is because since it is a electrophile, we want to pull away our electrons and help the electrophile accept electrons, because that's pretty much what the electrophile does. It accepts electrons. And so I'll give you some examples of electron donating and withdrawing groups in this next little table. So essentially, the biggest thing that tells us that something is an electron donating group is lone pairs and negative charges. And that is because both of these things mean that we have extra electrons, obviously. So it tells us there's a lot of electron density, which we are able to donate. And so some of these examples are NH2. And before I go on, just so you know, all this squiggly means is that this is what will attach to our group. So for example, if we have a diene like this, and we add this group to it, according to the way I've written it out, this diene takes the place of the squiggle. And so I'll leave this here in brackets just so you know what the squiggle stands for. So another example of a donating group just like that would be an OH or an OR group. And remember, the R can be any carbon chain. And we also have other electronegative atoms that can do this, but these are the main ones for now. Besides lone pairs, we also have R groups. So R groups are weakly donating, but they are still donating groups. And the difference between lone pairs versus R groups is that lone pairs donate via resonance, while R groups donate via electronic effects. So now that we have that down, essentially I mean any kind of R group whatsoever. So like propyl, a methyl, even like a ring structure such as this one, anything. But what you have to keep in mind is that the more carbons you have on your R group, the more donating it will be. So let's say we have a diene that has 2 methyl groups versus a diene that has something like this, right? These tert-butyl groups are going to have much, much stronger of a donating effect from all these carbons than this puny little methyl. So, as I said, more strongly donating. So yep, that's pretty much it for electron donating groups. Now for electron withdrawing groups, it's essentially anything that pulls away electrons. So the biggest hint that we have is positive charges, because we know that steals electron density, so that would be withdrawing. One example of a positive charge is NO2, and the reason that is a positive charge is because it would connect like so. Our nitrogen will have a positive charge, and one of our oxygens will have a negative charge, and so that will be a strong withdrawing group. And pretty much anything else with a positive charge. We also have our halogens. So any halogen attached, chlorine, fluorine, bromine, any of those. We also have our CF3. And not a halogen, but we also have cyanide. So that is also a withdrawing group. The last kind of category is carbonyls. So aldehydes, ketones, carboxylic acids, all of those. One interesting thing, though, is esters. So esters are kind of this in-between molecule. And in case you forgot, that is what an ester looks like. And we can connect this 2 ways. So if I draw it like so, versus like this, we're adding to opposite sides of the carbonyl group. So what I've drawn on the left means that our diene will connect to the oxygen side. And, excuse me. And we have some R group here. What this implies, or shows us rather, not implies, is that we have these electrons which can then donate into the system. So this ends up being an electron donating group. Versus in this case, it would attach to the diene on the carbonyl side. And our R group would be over here. That means that our electrons are going to just move this way. Not into the system. And I know a lot of you guys are thinking, well, wouldn't the resonance for this tell us that we go that way? And yes, it does. But we can also have some density go this way. So it's weakly donating, but it does still donate. And that's essentially the intro to dienes versus dienophiles and electron donating versus electron withdrawing groups. So now let's get into some mechanism stuff.